Hi everyone, we've been laying the foundation for understanding organic molecules. Been looking at their properties, their acidity, basicity, and stereochemistry, things like that. So now we're going to put all that together and study the reactions of organic molecules. So let's take a look at the first reaction. This one's called a nucleophilic substitution reaction, otherwise known as SN1. So S for substitution, N for nucleophilic, and 1 for first order reactions. That has to do with kinetics. So let's take a look at inside this box here. We have an organic molecule, R group, with some kind of a leaving group. These are any kind of portion of the molecule that can come off, dissociate. Okay, so the first step is for that leaving group to dissociate, which you can imagine that involves bond breaking and is highly endothermic. Can imagine that step is going to be our rate determining step. And what happens after that leaving group leaves is we get a carbocation intermediate because these electrons are being taken with the leaving group. So we have 1, 2, 3, 4 carbons left. One carbon is in the middle and the other carbons are out here. Now I do a dash and a wedge because once this is sp3, but once this leaves, I'm going to rehybridize this based on Vesper. You have a whole electron group missing, and so the whole thing rehybridizes into sp2. And you can imagine the p orbital here is now empty, and so we have a positive charge at this carbon center. I'm going to get rid of these p orbitals just for now, but hopefully you're picturing that they're there. So these other groups are just my methyl groups that are out here. So CH3, CH3, CH3. Now what happens after this carbocation is formed is that a nucleophile, which is usually electron rich, a Lewis base, can come in and want to bond with this carbocation. So just showing the mechanism here, the first step was that the leaving group left, dissociation, which is of high energy. This is high energy intermediate, carbocation, and then you have a nucleophile come in and attack the carbon that is positively charged. So that's considered step 2. So one of the possible products we get is where nucleophile comes in on this side and makes a bond to these 3 carbons. They rehybridize into sp3 again. Another possibility I'll show in blue, these can come over here. What if the nucleophile was on the other side of the carbocation? Then I would get this product. Now in this case, this is a chiral, but if these R groups were different, then I would have 2 different enantiomers. So if chiral, it's going to produce enantiomers. And the enantiomers will occur in a 50-50 ratio, or close to it, and that's called a racemic mixture. If we have a racemic mixture, is this going to be optically active or inactive? If you remember, optical activity is that rotation of light passing through a chiral sample. If we have 50-50, that means it rotates one way, rotates the other, and it cancels out. So in a racemic mixture, the optical activity will be 0 or optically inactive. Now just a little side point here. It's not super important to me that you know this, but you might be asked, if it's completely racemic, is it exactly 50-50? And the answer is no. Saul Winstein at UCLA, I think, is famous for discovering that when the leaving group dissociates, you're more likely to have a nucleophile come in on the opposite side because the leaving group is taking up space on one side. So nucleophile is more likely to come in on the other side. For our purposes, though, we'll go ahead and assume the leaving group is far away and the nucleophile can attack on either side. So if we think about the energy diagram we would get with such a reaction, let's say we have potential energy here and the reaction coordinate here, you're going to end up with a reactant that has a pretty high activation energy for dissociation. And then you form this relatively unstable carbocation. So it's going to look something like this. And then here's our carbocation, and we're going to have another step to get to the more stable products. So you're going to have bond formation and then something like that. Now, this first step has a pretty high activation energy compared to the second step. So once this is pretty reactive, it's going to go ahead and finish off. So this part here is called our rate determining step. It's the dissociation of the leaving group. Might help to write that out. Let's write that in as our notes. Now in the second step, it's just acid-base reaction. Nucleophile comes in. There's some lot of pull that these two are very attracted to each other. So it's a relatively fast step here. So the second step I would call nucleophilic attack. We use that term for the nucleophile bonding to what we call the electrophile. Carbocation intermediate is what we call the electrophile. Now take a look here. It says, was the nucleophile involved in the first step of the reaction? Let's take a look here. The first step of the reaction is dissociation of the leaving group. So no, the nucleophile did not do anything until after the carbocation was formed. That was the impetus for it to react. So I would say the answer to this question down here is no. Therefore, the nucleophile will not be involved in the kinetics because the rate determining step is whoever's involved here. So the leaving group is leaving this molecule. So sometimes we call this R-LG, or the molecule that later gives rise to the electrophile, or sometimes it's called the substrate. So whatever this starting material is, that's really what the rate is affected most by. So if I have more of these, then I'm going to have more of these and more of those, so reaction will be faster. But I can increase the nucleophile and it doesn't do anything for my rate determining step. So this is why it's called a first order reaction. So the rate is going to be dependent on only the substrate, RLG. Okay, or our electrophile. All right, another thing we want to look at is the carbocation. The carbocation is tertiary, and that's relatively more stable than something that's secondary. If I had a secondary carbocation, the energy might be higher, just a little bit. So that's going to, using the Hammond postulate, we're going to assume the activation energy is then a little bit higher as well. And if I had a primary or methyl carbocation, that's really much more unstable. We're going to assume that activation energy is higher than that. So the more stable this is, the lower it's going to bring that activation energy, assuming that this structure is similar to that one. So there's a correlation here between their energies. So if I bring one intermediate up, the activation energy goes up. If I bring the intermediate energy down, then the activation energy will come down. So it'll be faster. So we tend to favor forming things that are more stable for that reason. Therefore, let's think of all these different starting materials. Instead of this molecule, what if we started with this one? So think about that first step. What was that again? That was dissociation of the leaving group. So let's try dissociating this leaving group. And you will get a carbocation, and I'm just going to redraw it. I don't like to have this showing and then the positive on there. I would rather just show what forms separately. Okay, so this is what forms when this dissociates. So this is a primary carbocation, but it's next to the ring, so it's primary benzylic. Now primary benzylic is pretty stable because of the resonance from the ring, whereas normal, regular primary would not be. So keep that in mind. Let's keep going here, and I want you to go ahead and look at the substrate, and it's usually an alkyl halide, but not always, and note what kind of carbocation would form. This one would be primary carbocation. And then if it's allylic, vanillic, aryl, or benzylic, go ahead and add that as well. All right, guys, so what I started doing here was dissociating the leaving group, and you can tell what the leaving group is, usually a halogen or some kind of, we'll learn, tends to be a weak base after it dissociates. So here, So secondary for this, because there's 2 carbons attached to this carbon after this leaves as water. Methyl, tertiary, aryl, secondary, primary, allylic. Now remember back a few lessons, we were learning carbocations, and we said primary and methyl and vinyl and aryl were just very bad, so very high energy. Okay, so that means that if this is very high energy, the activation energy for forming that is going to be very high. It's not going to be likely to form. So let's find all those high energy carbocations and cross those out. The other thing you want to consider is whenever you form a carbocation, it can always rearrange to something more stable. So let's take a look at the remaining ones, and are there any here that could become more stable with a rearrangement? Go ahead and think about that, and I'll give you a hint since there's 3 of these. I'll give you this one here. In G, once this leaves, I notice a benzylic position right next to it. So I'm thinking of changing that carbocation from secondary to secondary benzylic. So see if you can find all 3 carbocation rearrangements, and then I'd like you to write them down here in the space showing the mechanism for that rearrangement. And here we go, guys. So for C, I noticed this could be changed from secondary to tertiary, and H as well, same kind of thing. So here I've drawn out those rearrangements. Okay, so go ahead and take a look at those and see if they match with yours. In the next part, we're going to work through a kind of SN1 that involves more than just 2 steps. So this is with an alkyl halide. So first step is dissociation of the leaving group. And I'd like for you to write out a phrase describing step 1 so that you really understand what that means. So what does this arrow mean? This means the leaving group is dissociating. Then go ahead and draw the carbocation that you make and do the rearrangement. And then stop there and let's check back on that. Alright guys, so what we have here is a secondary carbocation that forms, but you always want to look for possibility of rearrangement at this stage. And if you can make something more stable, then go ahead and do that. So we have a hydrogen neighboring that will then is in the benzylic position, can be shifted over. And remember, a lot of people draw the arrow the other way, so make sure you're drawing it the proper way. The electrons from the hydrogen move over and make a bond to the positively charged carbon. That leaves a deficiency on this carbon, so that's where the positive is going to be. This hydrogen is still on there. I just didn't draw it, but it's still there. And then you have the hydrogen that's shifted over now on this carbon, which I've circled. So this is called a 1,2 hydride shift. And you don't always see that, but you have to be in charge of looking for it, okay? And if there's no shift, there's no shift, but go ahead and look for that. All right, our next step is, now that we've made the carbocation, so we had an extra step because of the carbocation rearrangement. But now we're back on track with step 2, having that carbocation intermediate right here, and then doing the nucleophilic attack and finishing this off. So let's look at what's going on here. In step 3, we have water, and water's got these lone pairs right here. So that's considered areas of electron density that can react with this area of electron deficiency. So what we have here is an example of a nucleophile, which is water, and an electrophile, which is this carbocation. Okay, so they're going to get together like an acid and a base. So this is going to take a lone pair and attack that electrophilic carbon right here. And I'm going to get rid of this arrow just so it doesn't get confusing. So the mechanism arrows here are just lone pair attacking this positive charge. So you're going to have water here. Now I got rid of the other hydrogens, but they're still there. I just didn't want to show them. Okay, so that's it. Like, that should be the end. But sometimes when you get to the end, those are still not quite stable enough. So if you take a look at this molecule, it's actually a strong acid. These hydrogens, it's like hydronium ion, H3O+. So except you have an R group here instead of an H. So what we want to do is stabilize this by neutralizing it. So think of this as an acid. What you need is another base. Well, this part is sort of tricky for students. You don't have one water molecule. You've got billions of them, right? So it's up to you to bring them in as needed in these reactions. So notice water's drawn again, even though they didn't tell you 2 water molecules would be needed. That's sort of something in chem, that we just bring in molecules that we need if they're in the solution. So here's water. So this is going to grab a hydrogen, doesn't matter which one, and it's going to break this off. And this is just an acid-base reaction, right? Here's your base, grabbing an H+, and here's that follow-up where the bond breaks and goes on to the oxygen, neutralizing it. Okay, so that shows then our OH group, and what we have is now this water grabbed an H and became H3O+, which you can write H3O+ or draw out as I'm doing. And then overall, we had that bromide that came off in the first step. So we generally like to balance this out. So we show where, where everything goes, just following the law of conservation of mass. There you go. Okay, so oftentimes we don't always write these side products because we're interested in this molecule, but it is good just to know that they're still there. So how many steps was this reaction? If you take a look at it, you have that first bump, right, to our intermediate, and then you got another one going to a more stable intermediate, then you got another one, and these are pretty high energy here, and then you finally stabilize it by neutralization at the end. So this is 4 steps. So the energy diagram for this would probably look something like this. So just put your starting material somewhere like here, and then you've got this first step, which is very has a high activation energy, so our rate determining step. And then we're making a secondary carbocations, and most carbocations are pretty high in energy, right? So they're going to go up here somewhere. But I'm rearranging this to a little bit more stable carbocation, so I'm going to go like that. So here's my more stable carbocation right here. And then my next step is nucleophilic attack to make this acid. So this is a little more stable, just it's got an octet now. And then I've got this last step, which is neutralization to something way more stable. So I'm just going to do this last one like that. Now, I don't really know that it looks exactly like this, but this is just sort of an idea. It gives me my rate determining step being this first step, highest activation energy. I have pretty unstable intermediates right here because they're all positively charged. And then I've got my final product down here. So for these parts, let's go ahead and do a step-by-step electron pushing mechanism, just like up here. And the common mistake students make is they try to do all the arrows together in one structure, but notice how they did one arrow and then they showed what they got, and they did more arrows and they showed what they got, and they did another arrow. So try to break it out and show your mechanism step by step. And let's go ahead and do the first one together, and then I'll have you do the second one. So for the first one, I'm looking at this molecule here. This is my starting material. And the first step in SN1 is to dissociate the leaving group. So I'm not even looking at the NABR at this point. So later I'll tell you how you know that this is SN1 so that you know when to do that. So after the first step, we get a carbocation here, which is primary. Normally we wouldn't do anything after this, but this is allylic, so that stabilizes this primary. Otherwise it would stop here and you would have no reaction, unless you could do a rearrangement of some kind. So now we have this, and notice that the nucleophile is going to come in and attack here. Now a couple of things here. First, what is this nucleophile? NABR. Anytime you see sodium or potassium salts, go ahead and dissociate them because this is in some kind of solution. And normally the bromide is what's the important part. The sodium is a spectator ion. So for bromide, this is technically our nucleophile. Okay, so that bromide equals nucleophile.
All right, so if bromide is our nucleophile,
then it should come in and attack right here at the positive charge. This is the electrophilic carbon. However, do you guys see if I attack the bromine here, then my bromine's going to be out here. And then you might be wondering, how is this bromine on this side over here, and the double bond moved from here to here? So there's something going on here, all right? So what's going on, let's see if you can follow this. Maybe you can already see it. This
has a resonance structure. Let's go ahead and draw that resonance structure.
Now do you guys see what's going on here with the nucleophilic attack? So the bromide could attack here, and we'll get one product. The product we would get
is going to be something like this, right?
Okay, that's just really straightforward. You can see how this Cl got replaced with a Br and looks the same otherwise. But if you look at this product, it's not the same as that. So what's going on is the resonance structure is giving us a tertiary allylic versus a primary allylic. So this is going to be a little more likely to form. So now we've got our bromide ion
is our nucleophile, and we're going to attack our electrophile right here. And then that's going to lead us
to our major product here.
So this is what we would call our major product. And then sometimes you're asked to identify other possible products,
which we might call minor products. All right, again, when they ask for step-by-step electron pushing mechanism.
Electron pushing mechanism means show the step-by-step arrows that you're using.
So the curvy arrows that I'm using, I want to see this arrow here. I want to see this moving over here. I want to see this attacking right there. Those are the things that you need to do when you show a mechanism. All right, notice I broke it out. I didn't just show the Cl going out and the Br coming in at the same time. Okay, you need to show them in separate steps. So I'd like to see the intermediate separate, reasonable number of arrows, usually 1 or 2, and then showing another step, and then showing another step. So I'd like you to try that for this one, and go ahead and pause it, and then we'll come back and check how you're doing. Okay guys, we're back. What I did was the same thing as before. First step is dissociation of the leaving group. Then I got a carbocation that was secondary, and I noticed it was tertiary next door. So I did a hydride shift, got the tertiary carbocation. Now I used my nucleophile, which is methanol or methyl alcohol. That attacked the positive because I noticed that the methyl alcohol didn't go onto this carbon, it went onto this one. So it helps to look at what's going on in, overall. Okay, once I got that, then I had this very acidic intermediate. So here's where I had to know to bring in another methanol as a base and pull that hydrogen off. So that will give me this ether right here. So just to talk through some notes here, and by the way, a lot of students like to use colored pencils for this type of stuff because you can track a little bit better what's going on when you can see different groups are different colors. So if that helps you, go ahead and do that. First step is dissociation, carbocation rearrangement, and then this last nucleophilic attack, and then this last step is called proton transfer or deprotonation. Let's go ahead and write those in just so that you know what these steps are. Okay, so here we've got leaving group dissociation, then we had a carbocation rearrangement, then we had a nucleophilic attack, and then we had a deprotonation or proton transfer step at the end. So this is very similar to the one up here, same kind of thing, and that's because we are using an alcohol and we have to deprotonate it at the end to form an ether. All right, so we're getting to the end, and we want to look at some of the overall things about this reaction. 1, did the nucleophile have anything to do with step 1? Well, no. You can see that after the leaving group dissociates, then the nucleophile comes in. But in this first step, this was just sitting pretty there. And that's because it tends to be a weak base. It tends not to be able to do anything because of its stability. So it's not super reactive. So this tends to happen with weak bases. So
no, the nucleophile is not involved.
We know that step 1 is the rate determining step, and if the nucleophile is not involved, then it shouldn't
Be in the rate law. So that leaves us
with the rate law of K, rate constant, times the electrophile concentration.
Technically the electrophile is the carbocation, but you can call it RLG or you can call it substrate. I just call it electrophile because it's going to turn into the electrophile.
Does this mean the SN1 reaction is uni or bimolecular if the concentration of the electrophile is the only thing that matters in the rate law? So I would say that electrophile concentration is one thing, it's one molecule, so it's not both of these. So I would say that's
unimolecular.
Okay, for unimolecular or
First order reactions, it's another term that we use. First order reaction.
So using this rate law, let's see what happens if the nucleophile concentration is doubled. How does that affect the rate? Well, you can see that the nucleophile is not in the rate law,
so the rate doesn't change.
If the electrophile concentration is doubled, that will affect the rate. The rate will do the same because this is to the power of 1. So if the electrophile rate concentration doubles, then the rate doubles. And if you double the electrophile and double the nucleophile, what do you get? The rate should be doubled only because you put these two together. You have one that doesn't change and one that doubles, so you just have one that doubles. All right, so hopefully that makes sense to you. Finally, let's put it all together, everything we just learned about the SN1 reaction. SN1 reactions are substitution reactions. They involve
about 2 steps or more, right?
We've seen that. The leaving group leaves and then the nucleophile attacks.
So the molecule that becomes the electrophile
loses its leaving group,
forming a carbocation.
The first step will be faster if you form what kind of carbocation? More or less stable?
If you form a more stable
carbocation, that'll bring the energy of activation for forming that down. So let's take a look right here. More stable intermediate will have a lower activation energy via Hammond postulate. All right, in the rearrangements, they're possible because we have carbocation intermediates. If we didn't have a carbocation, there would be no way for them to rearrange. Pretty straightforward, right? In the second step, okay, the nucleophile attacks. And although we might not see exactly 50-50, we're going to say that for the most part, they're pretty close to 50-50. Okay, assuming the leaving group has dissociated and left the building. Okay, so if the product is chiral, are you going to get optically active or inactive mixture if you have attack of the nucleophile on both sides equally? I think we saw from before that because you can attack either way, you might have R and S available in both. So that will give us a racemic mixture or racemate of enantiomers, about a 50-50 ratio. And the reaction kinetics is going to be unimolecular. And so if we have a 50-50 racemic mixture, that's going to be optically inactive. All right, so hopefully you can follow that. And if not, go back and review the parts and ask me questions, okay? I'd love for you to say, how do you know this? Or why is it this way? So feel free and really learn this before you move on to the other reactions. Okay, do some practice problems, and then we will learn the next one.